Okay. Start sharing. Okay, so people can see my notepad. What the crap is this? I'm gonna do that. Alright, hopefully this works. People can see the notes yet, okay. Alright. So, let's start with the summary from last time. So we started to look at the calculus of variations. And we introduced the delta operator. Which we also call the variation. And let's say if we have a function f of x and a new function f bar of x that's equal to f of x. Don't understand why it keeps changing to a cursor. So f of x we call the unvaried function. F bar of x is f of x plus some small number times a new function. So f bar of x is a function that's kind of like f of x, but it differs in a small amount that one can tune by making epsilon bigger or smaller. And so we define the variation of f as f bar minus f, which is epsilon phi of x. Okay? Just for notational simplicity, we'll interchangeably use f and y of x. So if we have y, it's going to hit the bottom of the thing. We have y of x as a function. It's just the same as f of x. Alright, but then we'll write y instead of f of x. And we'll write delta y. So remember, delta y is really equal to epsilon phi of x. And we'll try to write the epsilon phi of x in the beginning, and then eventually you'll get the gist of it, and we'll just write delta y's everywhere. Okay, but remember that in principle it all comes from this idea here of varying a function by adding a small amount of another function. Okay, and so we noticed we looked at some properties. I guess I should point out that when we do these variations, delta x is always 0. X is the dependent variable. And so when we vary a function, we don't vary the dependent variables. It's x is the independent variable. I don't know why I go to mix those up. Independent. And so that means that delta x is always 0. So we looked at some properties of this delta operator. One property is the commutation with the derivative, so we found that delta of dy by dx is the same as d by dx of delta y. Similarly, we found that delta of the integral y dx is the same as the integral of delta y dx. And then we also saw the chain rule, delta of f of y, remember, this is y of x, is the same as, how do we write it out last time? It's the same as df by dy delta y. And if f is a function of multiple functions, delta f of, let's say, y, z, etc., where this is y of x, this is z of x. Then it's the same idea, it's just with partial derivatives. So that's df, di-f by di-y, delta y, plus di-f by di-z, delta z, etc. Okay? And we also found that the stationary value of a function that could be a maximum, a minimum, or an inflection point is given by the condition that di-f by di-qi, so f is now a function of q1, q2, etc., equals 0 for each I. Okay? Whether the q1s are functions of x, right? Or t if it's in the language of classical mechanics. So that's what we got last time. Okay? Any questions about that?
What's the little upside down A mean?
Oops. This thing here.
Yep.
It's a mathematical symbol, and it means, what's the meaning? I know in French and in English, but like for all values of I, or whichever value of I you choose. So basically for all I.
Thanks.
All right. All right, so let's take a new page. This thing's messed up. There you go. Just have to move it. People can see the page, like it doesn't look all garbled. I'll assume yes. So now we're going to look at the subject of constraints and Lagrange multipliers. This again should have been covered in calculus in your undergrad courses. But I'm sure you don't remember any of this if you haven't done it recently. I certainly didn't. So constraints and Lagrange multipliers. So these are useful. So remember, we found the condition for minimizing or finding the stationary value to give you a maximum. The stationary value of a function, but we didn't really have any constraints, right? So we said no matter where we are in the function of variables y and z, no matter where we are in y and z, we want to find the minimum or the stationary value of that function. But maybe there's a constraint in that you can't be anywhere in y and z, and there's some constraint equation that says, y and z have to lie on a circle or something more exotic. And so the question is, how do we find the stationary value of a function when it's subject to a constraint? So for example, this means you have a constraint that you're not allowed to freely vary the parameters. So let's say you have some weird shaped bowl. And you don't have to draw this. I mean, this is hopefully patently obvious. And we have a marble. And you're interested in finding the minimum of where this marble can be, so it's minimum potential energy, given, for example, some kinetic energy that's not enough to go over the bump, then you have a constraint here, because the minimum of this function, which is the bowl, is down here. And that we would call an absolute minimum. But maybe there's a constraint that the ball can never go higher than this. And so this is, let's call it a useful minimum. This is not a real term. And of course, so we've been interested in a situation mathematically that imposes this constraint so that we can find the true stationary value of this function subject to the constraint. Okay? So just because I'm running out of letters in the alphabet, if x is the dependent variable and I keep using y and z instead of x, I'm going to use q's instead. So just notation-wise, notation. So the dependent variable, the independent variable, will either be x or t, and the dependent variables will be called q's. So they'll be either, what does that sound? Interesting. Either q of t, q of x or q of t. And this will allow us to have multiple q's. Okay? So the question is, the problem we want to solve is we want to find the stationary value of some function f of q1 q2, etc., subject to the constraint that some function little f of q1, q2 equals 0. Okay? So remember back when we did a couple of mechanical examples, we could write a constraint equation as an equation between the variables that's equal to 0. So the connection to mechanics is that Q are the generalized coordinates, and maybe, you know, our bead was stuck on a rod, and so there's a constraint between the generalized coordinates, what values they can take. So there's two options. The first option to solve this problem is to use the constraint equation to eliminate one of the Q's, right? Presumably, I can use this equation to say Q1 equals something that depends on the other Q's. And then I can sub this back in to here, and then F would be a function of only Q2, etc. And then I could just apply the condition that we had before and set its partial derivatives with respect to all the other variables equal to 0, and then the problem is solved. So, and then this is a perfectly valid situation, and it works, okay? But the problem is, or an issue really, is which Q to eliminate. It's arbitrary. Let's say you have a mechanical system, and it's really arbitrary to eliminate X or Y. Why all of a sudden do you eliminate Y and pretend that you know, X is more special than Y? So it's aesthetically not as pleasing, and it's also not as easy to generalize. So this I assume you know how to do, right? And it's literally just substituting back into the original function. So that's not what we're going to do. What we're going to do is what's called the method of Lagrange multipliers. Oops. Lagrange. And that's what we're going to do. Okay? So remember, we have this constraint equation, little f equals 0. So that's an equation between that ties the Q's to each other. And then we want to minimize or find the stationary value of f. So what we want is delta f, which is di f by di q1 delta q1 plus di f by di q2 delta q2 equals 0, given f, little f equals 0. Now, we can't just do what we did before and set all of these partial derivatives equal to 0. Remember, the condition that we had to find that all of these partial derivatives equal to 0 was that we could vary these delta q's independently. So we imposed the condition that we had this vector alpha, and no matter which direction we walk in space, that delta f or f should not change. So what that's saying is that we can vary the delta q's independently of each other, and no matter which direction in the q space we go, f should be stationary. That's no longer true because the q's are not independent of each other because of this constraint equation. We can't just walk in any direction. We have to walk in a direction that's in harmony with this constraint, right? Maybe you have to stay on a circle, and so you know, the q's are constrained somewhere. They cannot vary independently. So it's important to note that we cannot vary delta Q's independently. So this is our method. This one at the bottom of the page here. New page 3. So what we do is, remember we had delta F, which was that sum of terms, equals 0. Since F equals 0, that also means that delta F equals 0. So delta F is di F. Oops, that's a little F. Di little f by di Q1 delta Q1. Alright. Di little f by di Q2 delta Q2 plus etc. equals to 0. Alright, both of these things are equal to 0. Except that you can't vary the delta Q's independently. But the sum of them is still 0. Right? So what we can do is we can add 0 and 0. Actually, what we'll do is we're going to add 0 plus lambda times 0. That's still equal to 0. And this lambda is what we call a Lagrange multiplier. It's a very clever technique that Lagrange came up with, and you'll see why it's so clever in a second. So what we do is delta F plus lambda times delta little f equals 0. That gives us an equation, right? So delta F is the sum over I to n of di F by di Qi delta Qi, all right, plus lambda di little f by di Qi delta Qi, and that's equal to 0, right? This thing here, for example, is just the sum of the di s by di Qi's delta Qi, right? And this one here can also be written as a sum from I equal 1 to n. Okay? So now, well, we can write this out as one term, because the delta Qi's are the same, right? And the sum is over the same number of terms. So that's di F by di Qi plus lambda times di little f by di Qi, and the same. Equals 0. So if we go back to the unconstrained case, right, the argument that we made was that this term didn't exist, right? So we just had the sum of the di f by di Qi times delta Qi, and delta Qi was the epsilon alpha. We said that no matter what choice we make of alpha in all coordinate directions, this sum has to be 0, and that can only be true if it's regardless of this term. That can only be true if each of these terms is individually 0, right? So for the unconstrained case, recall, I think, Michelle, you could be muted if you're not talking. For the unconstrained case, we had the sum of di F by di Qi delta Qi equals 0 regardless of I, and so regardless of delta Qi, And so we found that di f by di qi is 0 for all I. Alright? That's no longer true now. We can't take arbitrary choices of delta qi's because one of the delta qi's has to depend on the other delta qi's. Okay? So we can't just vary them independently. So these terms are not identically 0. So what we do is we choose the term where I equals n and set it to 0. So we choose di f by di qn plus lambda di little f by di qn equal to 0. And that's an equation that gives us lambda. So we choose lambda such that this term here equal to 0. Okay? So we've now chosen lambda on purpose. Right? We just added this arbitrary constant in here. It's our choice, right? It's 0 plus something times 0. So we can choose that something so that the last term is equal to 0. Now, this should be an us, not a use. So just to be explicit, so we choose lambda such that this term is 0. So now we've effectively eliminated delta qn, or qn, from the equation. So that means now that the sum from I to n minus 1 of di f by di qi plus lambda di little f by di qi times delta qi equals 0. So I'll even use red. This is n minus 1 now, because the last term is 0, right? The nth term is 0. We chose lambda on purpose so that that term would be 0. So now we have n minus 1 q's in here, and they're all independent. So now this is 0 regardless of delta qi for I equal 1 to n minus 1. So now they are independent. So now, only for the case I equals 1 to n minus 1, we can vary this freely. That means that these terms must now be identically 0. And so now we have the di f by di qi plus lambda times di little f by di qi equals 0 for I equals 1 to n minus 1. So we have two equations, right? We have this one equation on the nth term where we have di f by di qn plus lambda di f by di qn equals 0. And that's the equation that defines the lambda. And then for all the other terms, we can vary these guys independently. And so for all the other terms, di f by di qi plus lambda di little f by di qi is equal to 0. And so the problem is now solved, right? Well, of course, the pure genius in this method is that these two equations are the same. At least they look the same. We've given this one a different meaning. We're saying this is the equation that determines lambda, and then this is the equation that's true for all the other i's, up to n minus 1. But the equations actually look the same, right? I could just say di f by di qi from plus lambda di little f by di qi equals 0 for all I, because it's true. It's also true for the last I. And that's the true genius in this lambda multiplier, like Lagrange multiplier thing. Okay, so what this means is can minimize a new function, let's call it f bar, that's f plus lambda, the constraint. Okay? And now we can apply, we can vary the parameters of f bar freely. So the stationary condition is this, just as we had in the unconstrained case, for all I equals 1 all the way to n. So this gives us n equations, but we have, of course, another unknown, which is lambda, and lambda you can get from the constraint equation. Does that make sense? We've basically added one extra parameter that makes us handle this constraint equation as an additional equation that gives us that parameter. So we included this constraint equation into our final function. So this is all super obscure. So how can one actually use this? So let's do an example. And once you see the example, then hopefully it's actually quite obvious how to do this all the time. So this is example in the notes. It's example 2.3. So it's I guess a mathematics example. So we want to calculate the dimensions of the box. And we'll call those dimensions x, y, z, subject to the constraint that the area of the box is 2a. Of course, this is a stationary value problem, right? So we want the dimensions of the box x, y, z subject to the constraint that, in this case, let's say that maximize the volume of the box. So in other words, you have a limited amount of cardboard, and you want to make the box that will hold the most stuff. All right? So let's put this back into our language of variational calculus and Lagrange multipliers. So we want the stationary value of the function f that's x times y times z. All right, that's the volume. Everybody agrees the volume of a box is the 3 coordinates of the box, okay? And it's subject to the constraint so the area of the box, all right, so the box has 6 faces. It's a box that you can close. So there's two faces that have dimensions x and y. There's two faces that have xz, and then there's two dimensions that have yz. So the constraint is that we have 2 times xy, so the area of the box, right, plus, let's do it in the same order, 2 times xz plus 2 times yz equal 2a. Right, so I said the area of the box has to be 2a. It was a little bit arbitrary that you just put the number 2 in there for no reason, but now you see why I put the number 2 in there. Right? So the constraint equation, remember, we want to write it in terms of, we want to write something that f equals 0, right? So if I want to write it in that form, f is equal to xy plus xz plus yz minus a, right? And that's equal to 0. So we have our two functions, right? We have f. Like I said, I could have noted that f is a function of x, y, and z. So that's like q1, q2, q3. And then little f is also a function of x, y, and z. And it's equal to that. So the method of Lagrange multipliers tells us to build the function f bar, which is f plus lambda f little f. All right? And so this f bar, that function is f, which is xyz, plus lambda times xy plus xz plus yz minus a. Right. This is the function that we want to find the stationary value of, where we can now vary x, y, and z independently, even though x, y, and z are in fact dependent on each other because of this constraint equation. So we want to find the stationary value of f bar. So to find that, I do all the partial derivatives, because f bar, I can vary all the variables independently. So di f bar by di x, that's got to be equal to 0. So di f bar by di x is, first term is yz, and then it's lambda times y plus z. And that's got to equal 0. That's one equation. Di f bar by di y. So that's xz plus lambda times x plus z. And then finally, di f bar by di z, that's xy plus lambda times y plus x. Okay, so here we have 3 equations. Four unknowns. All right, we don't know x, y, z, and lambda. However, we have one more equation, which is the constraint equation. This guy here is also an equation that we can use. So we also have, finally, xy plus xz plus yz equal a. plus 1 equation from the constraint. Okay? So we've effectively added this Lagrange multiplier so that we can add an additional equation and treat all the variables as independent. And so now, that's 4 equations, 4 unknowns to find x, y, and z. So that's hopefully something that you can do. So if I call these equation 1, 2, 3, and 4. One way to do it is to multiply equation 1 by x. So that gives us x, y, z plus x times lambda y plus z equals 0. And multiply the second equation by y, I get x, y, z plus y times lambda x plus z equals 0. And if I multiply the third equation by z, I get x, y, z plus z times lambda times y plus x equals 0. Alright? So this stuff that you should be able to do, right? So let's use these two equations to equate. So both these equations have x, y, z in them, right? So on this equation here, x, y, z is equal to lambda x times y plus z. And in this equation here, x, y, z is equal to y times lambda x plus c. So if I equate these two, I get x times lambda x, y plus z equal to y lambda times x plus z. So in this equation here, the first term, x lambda y, also appears in the second equation, x or y lambda x, right? That term actually cancels from both sides, and we have on the one side x lambda z equals y lambda z, right? And then here the z's I can cancel out as well. And then I get x lambda equals y lambda. And so there's two possibilities. Either lambda equals 0 or x equal y. Alright, x is not necessarily equal to y, because lambda can be equal to 0. You have to be careful when you divide by a number, right, out of an equation. So this would have been wrong if z equals 0. So these are both valid solutions. So these will give, when you substitute them back, different answers, right? If lambda equals 0, what you'll find for this to be true, if lambda equals 0, that means this term here is 0. And so if lambda is 0, this term here has to be 0 as well. And these equations are all the same, and so what you'll find is that x, y, and z are also equal to 0. And this is a perfectly valid solution. X, y, it's an infinitely, well, one of the variables will not be 0 because of the a here. Sorry, so they're not, what happened? One of these will not be 0. So what you have is a box that has the correct area, but it has an infinitesimally small volume. And so the volume is 0. And that's a true stationary value of the volume, right? What we're finding here are the stationary values of f, the volume, subject to the constraint. And one of the possibilities is that the volume is minimal, and you actually have a box with no volume and just area. So it's just one sheet of cardboard of area 2a. All right, so that's not the solution we're interested in. So we're interested in the other solution, and that's the solution where x equals y. And from the symmetry of the problem, what you'll find is that x equals y and y equals z, and z equals x. And so if all dimensions are equal, then we get a cube. So that's the one we want, and the answer is a cube. And so then I can let you do the math, and it's written out in the notes, but you can go and figure out what the dimensions are. And the dimensions that you get are that x is equal to the square root of a over 3. So that part's just, high school math. So stepping back and thinking about it, we use the Lagrange multipliers to find the stationary value of a function given a constraint. And then we found that we had the n variables plus lambda to solve for, but that's okay because we got n equations plus one equation for lambda. We were able to treat all the variables independently, and at the end we found more than one solution. That's because this method gives us stationary values, and we can find minima or maxima or inflection points. And so then we have to use our brains a little bit to figure out which solution we're actually interested in. And we found a solution that the shape of a box that maximizes the volume for a fixed area is a cube. So that was to make the Lagrange multiplier method a little bit more concrete with an example. Any questions about this? So in the sake of completeness, we're finding the stationary value of a function when there's multiple constraints. With multiple constraints. So again, we want stationary value of f, which depends on our q's, subject to k constraints. Constraints. So now instead of having one constraint equation, we have k constraint equations. So the constraint equations we'll write as f, little f1 of the q's, q1, q2, q3 equals 0. f2 of q1, q2, etc. equals 0. f3, q1, q2, etc. equals 0. And we'll have k such constraints. Okay. And so this is, again, you could have a classical mechanics problem where there's more than one constraint between the variables. Maybe the bead is supposed to be on a circle, and that circle moves in a well-defined way. And so then there's more than one constraint. Okay, so how do we handle this? Well, very much the same way. So in principle, we have n variables, k constraint equations, and so in principle we have n minus k degrees of freedom. And again, the issue here with the Lagrange multipliers, so we can use our constraint equations to eliminate all the variables, right? And then we truly reduce the number of degrees of freedom by having only n minus k in the language classical mechanics, n minus k generalized coordinates. But maybe aesthetically or practically, it doesn't make sense for us to eliminate those variables because maybe they have a meaning and we want to examine their meaning through the equations of motion. Also, some variables, it's arbitrary. It could be arbitrary which variables you eliminate using the constraint equations. So maybe you actually want to keep the n degrees of freedom or your n variables in your problem, but you want to somehow handle the constraints so that you don't favor one of the variables over the other by arbitrarily eliminating them. And so again, that's a situation where the Lagrange multipliers are useful. So we're just going to do the same thing that we just did, except now we're going to have several of these functions, right? So again, remember that delta f is 0, delta big F, sorry. And then delta f1 is equal to delta f2 equal to delta fk equal to 0. Okay? So we construct again, arbitrarily we can say that 0 plus 0 plus 0 plus 0 plus 0 is still 0. So we construct a new function, or we construct a new quantity that's still equal to 0, given by the sum of I to n di f by di qi plus lambda 1 di f1 by di qi plus lambda 2 di f2 di qi lambda k di fk by di qi delta qi equals 0. All right. So this term here, di f by di qi. I guess you can't see my pointer, right? Let's just use the red. This term here is this term. This term here is this term, etc. Right? So we've just constructed delta capital F plus lambda 1 delta little f plus lambda 2 delta f2, etc. equals 0. And because each of these are 0, we've just said that 0 equals 0. But we've added in a bunch of lambdas that don't change the result. So we did exactly the same thing that we did. Well, so I just thought it was a question from Jimmy. Do you still have that question, Jimmy? And what? I'm not sure. It looks like a... Okay. Sorry, I don't always catch the question. So you can, if you like, press the raise your hand button on the collaborate session, it makes a little ding noise that could make me notice that you have a question. But otherwise, I'm not usually looking at that window. Okay. So like I was saying, we just constructed the same thing we did before, except now we have k constraint equations, and so we introduced k lambda Lagrange multipliers. So again, we cannot vary the delta q's independently. So these terms are not the term in brackets is not identically 0 for all values of I, because the delta QI's are not independent from each other, from one I to the other. The delta Q's depend on each other through the constraint equations. However, we can choose our lambdas so that we get certain of these terms to be 0. So let's choose the nth term. So that's di f by di qn plus lambda 1 di little f1 di qn plus lambda 2 di little f2 di qn, etc. Lambda k di f little fk by di qn equals 0. And we can make k of these equations. So the n minus k term, that's di f by di q n minus k plus lambda 1 di f1 divided by di q n minus k. I'm going to skip that one, plus lambda k di fk di qn minus k equals 0. So I've written out the nth, so the n minus k to the nth term. I've just written them out explicitly. And so we do the same thing here. We choose lambda 1, lambda 2, etc. to lambda k to make these equal to 0. All right, so they weren't necessarily equal to 0, but we choose the lambda k, so we have k equations, right, from n minus k to n. We have k equations that allow, and the lambdas are independent, so we can choose those k lambdas so that these k equations are satisfied and equal to 0, right? So we can choose that. This is up to us to choose it. Okay? Let's underline choose in red. So now, we go back to our original equation here. The n minus k terms, the last k terms, sorry, from n minus k to n, the last k terms are identically 0, right? So our sum becomes from I to n minus k minus 1, right? I think that's correct. Where is it? No, this is the n minus k plus 1, so that's n minus k. I think. So for these first terms, the first n minus k terms, you have di f by di qi plus lambda 1 di f1 by di qi, etc. plus lambda k. Give ourselves a second with this thing. Lambda k di fk by di qi, that whole thing times delta qi equals 0. And now pay attention that we only have the first n minus k terms here. So because we've eliminated the k last terms, the first n minus k terms are 0 independently of these delta QIs, right? So now I only goes up to n minus k, and these delta QIs can now be varied independently. And so if these can be varied independently and the sum has to be equal to 0, that means that each term in the brackets is identically 0. And so what we find is that di f, what just happened there? Di f by di qi plus lambda 1 di f1 by di qi plus etc. plus lambda k di little f k by di qi is equal to 0 for I equals 1 to n minus k. And so now we have these n minus k equations here, and then we have these k equations here, right? These ones here, sorry. Here we have k equations. Here we have n minus k equations. So we have a total of n equations and n plus k unknowns, because we also have the lambdas that are unknown. But then we have the k constraint equations, and so we really do have n plus k unknowns and n plus k equations. And so of course now if you compare the equations, the k equations that we use to set the lambdas, that got all garbled up here, those are in fact the same as the equations for I equals 1 to n minus k. And so of course that's the whole point of the Lagrange multipliers, is that you get the same set of equations. I don't understand why OneNote keeps shipping. Let's add another page here. So what we can do now is we can construct a new function f bar that's equal to the original f plus lambda 1, the constraint equation, plus lambda 2, the second constraint equation, plus all the way to lambda k. And we can treat the QIs as independent for f bar. So that means that di f bar by di qi is equal to 0, and that's n equations. And then we also have the fi equals 0. That's another k equations. And so then we have n plus k unknowns. That's the q1 through qn, and then the lambda 1 through lambda k. Okay? Any questions about that? So we'll finish by motivating our next thing that we want to do, and then we'll do the derivation of that next time. So by the way, what we've done so far, we could have done with normal calculus, right? We didn't need to introduce these deltas as these variations. The Lagrange multiplier and all this stuff can be handled in normal calculus. And in principle, you've done this in your undergrad math classes. So the true subject of variational calculus is finding the stationary values of an integral. And in the mathematicians, we call this a functional. Mathematicians jargon. So consider an integral which we'll call I for integral of some function L that depends on other functions. And what we'll use in particular is a function that depends on y prime, and x. So y is a function of x. Y prime is dy by dx. I think we've used this notation before. Anyway, it's common in calculus, right, to denote the derivative with respect to x with a prime. And then x is the independent variable. So we want to find the function y that makes I stationary. And so when I mean it makes I stationary, maybe it means make it a maximum or a minimum. So we want to find which function y makes this integral stationary. All right, given L as a function. So why could we possibly care about doing this? I guess I'll start a new page. So I'll give you an example of a case where you may want to find a function that maximizes an integral or minimizes. So this is example, what is it called? 2.4. I'm only going to spell this once. It's called the brachistochrone. Okay. And it's actually the original problem that was used to derive or come up with the formalism of variational calculus. And it's a very important problem. So this is the problem. Let's set up a coordinate system here. And this is a real world, so we have gravity. And we have 2 points, A and B. And we have a wire and a bead with a hole in it. We want to bend the wire so that the bead will fall with gravity from A to B in the shortest possible amount of time. So we have a wire here. Could have any shape. Let's make it B bigger. We have we can make the wire go all the way down and back up, or up and then down, although that's probably not the best choice. I want to find the shape of this wire so that some bead here takes the shortest amount of time to go from A to B. All right, so presumably there's a solution of the optimal shape of this wire. It might be a straight line, or it might be something more funky, and we don't know. And the answer is given by the problem of finding the stationary value of an integral. So the total time, oops, and so we want, of course, the wire has a function, will have a shape, and that function of the shape of the wire will be y of x. So we want y of x that minimizes the time. Okay? So the total time, t, is going to be given by an integral from a to b of ds over v. So ds is a small element along the wire, right? And so, of course, you know, you have v equals x over t if you want. And so t is x over v, right? So ds is a small element of the wire that the bead goes along, and then at some point along the wire it'll have some speed v. And so the total time is the time it goes from along this little piece of wire, the first piece, then the second piece, and the third piece. And so you make the pieces of wire infinitely small, and so that sum of infinitely small pieces is an integral. And so the total time is the integral from a to b, I use capital M, little letters here. It's the total time to go over all the segments, right? And so that's given by an integral. And so now, because there's gravity, of course, v depends on x, or in principle on y as well, right? The x, there's a constraint of this wire, which we don't know, but given x, one will be able to find y because the bead is on the wire. So the speed is a function of x. And it's also a function of y, or a function of y. So what is the speed? Let's say the bead starts here at, oops, at a height ya, and at some point in time it's at a height y. So we can use conservation of energy to find the speed of the bead as a function of y. So the total energy, or the kinetic energy, if the bead starts at rest, is a half mv squared. And that's equal to mg times ya minus y. Right? That's just conservation of energy. So now we know how the speed, v, depends on y, right? It's the square root of 2g times ya minus y. Now we need to convert this, so we want this to be an integral over x, because we want y of x, right? So this is like a neat little trick. So ds is equal to the square root of dx squared plus dy squared. All right, I can break up this little ds here as a dx and a dy. And so the length of ds is the square root of dx squared plus dy squared. And I can do some more mathematical trickery and write this as 1 plus dy by dx squared times dx. So I just divided out the dx squared and took it out. And if we use the notation of primes, that's 1 plus y prime squared dx. So if we substitute both these guys back into our integral, the total time t is the integral from a to b of ds, which is this thing here. So that's the square root of 1 plus y prime squared divided by v, which is the square root of 2g ya minus y. And so just to be explicit, here we want to find y of x such that t is a minimum. So that is exactly the problem that I told you we might want to face is we have a function, so it's 1 plus square root of this whole thing here, a function of y and y prime, and we want to find the condition of y of x when it creates that you want to minimize an integral. And so this function, this L of y, y prime, and x is this 1 plus y prime squared divided by 2g ya minus y. And then we want to minimize this integral that's given by L dx. All right. And I'll leave it at that. So I motivated the problem of how do we solve for y of x such that this integral of L of y, y prime, and x is stationary. And we'll start with that next week. Any questions about that? Okay, so next week I'll be in Vermilion, but I'll either teach from my office or maybe from the classroom. But you don't have to go to class. And then the other thing I wanted to note is that there's an assignment that's due next week, and the assignment is posted on the Moodle, right? If you have any questions, please ask. If you want to have it marked, you have to hand it in by the deadline, right? Remember, you have the choice to not hand in assignments, and then your exam is worth more. But if you do want the assignments marked, then you have to hand them in by the deadline, which is next Friday for the first assignment. Yeah, if there's any questions about it, ask me. The assignments will be handed in. You have to scan them and submit a PDF file through the Moodle website. I hope that will work. The PDF file is limited to be 2 megabytes, so you can't send me a 8 megapixel scan of your thing. Okay. If there's no more questions, that'll be it for today. Okay, thanks everyone for joining. We'll talk to you on Monday. Bye.